Hey, welcome to Physics 1403, Stars and Galaxies. This week in class, we're going to be talking about the nature of stars. We're going to be talking about a lot of different things, for example, what powers a star and how we classify stars using a system based on their surface temperature. And we're going to be looking at the effect that mass has on a star. But before we do any of that, we probably need to define what a star is, because I think that's the most important thing to get started with. And I've written this definition up on the board. I didn't make it up, someone else did. All right, it said a star is a sphere of gas held together by its own gravity. It is a self-luminous black body that shines by radiation derived from internal energy sources, specifically nuclear fusion. All right. As a reminder, we talked about black body radiation before. A black body is an object that, for all intents and purposes, does not reflect any external radiation. For example, our sun is a black body. All the light that we see coming from the sun is coming from internal energy sources to our sun, just like any other star. Whereas you take something, for example, like a nebula or our moon, those may have external energy sources that are illuminating them. Those may have, whether it's a nearby star that is energizing atoms in the case of a reflective, sorry, I forgot which one it was, but you can cut that out. So in the case of a emission nebula. Okay, in the case of so uh, so whether it is an emission nebula, which is basically a ball of gas that is lit by external energy sources, radiation from a hot, dense star that is nearby, that's energizing and energizing all of those electrons, or a reflection nebula, which is really more like a diffusion effect. But those light sources don't come from internal sources. So that's why they're not stars. Okay, so our sun is a star. Every star that is visible in the night sky is actually part of our galaxy, the Milky Way. And our galaxy has about 200 billion stars. It's a pretty average sized galaxy. Nothing particularly special about our star. But we do use our star as reference for other stars, particularly when referencing mass. All right, so here's kind of what's happening. So when we're looking at this, I want to take this definition and I want to break it down a little bit. All right, so a star is a sphere that is held together by its own gravity. That's really kind of a neat thing if you think about it, because stars have all this energy that's being emitted from inside their core. The energy from our sun started at the core of our sun and has been working its way out for millions of years. All right, trying to get through all this dense material, all this dense. Most stars are usually about 74% hydrogen, about 24%, 24% helium, and about 1% other stuff. So that would be the rest of the periodic table. Anyway, so what holds the star together? The gravity is constantly pulling down. And so I think a legitimate question to ask is why doesn't a star continue to get smaller and smaller under its own gravity? Well, the simple answer to that is internal energy sources. This fusion is putting out a lot of gas pressure. And this gas pressure is pushing out on the star. And so as you have gravity pulling down, gas pressure pushing out, and those two things are in balance in what we call a dynamic equilibrium. And this equilibrium then is what makes the star the size that it is. In fact, stars actually do change size over their lifetime, and we'll talk about that a star has a birth, a life, kind of a midlife crisis, and then finally a death. And that they do change size. For example, when we talk about birth of star, we'll talk about protostars that are much larger than stars, and they shrink down under their own gravity. And until that internal energy is providing the equal amount of external push, and then they stop shrinking. As a star gets older, then it starts to get bigger and bigger because it burns fuel. It goes through its natural hydrogen and then helium and carbon and all these other fuels. And as it does so, it gets lighter. And as we've talked about in class, the lighter something is, the less mass it has. or the less mass it has, the less gravity it has. And so that means that that gas pressure pushing out has less gravity to pull against it. And so stars, after their birth, go through a very slow expansion process that lasts billions of years. And eventually, our star will become a red giant, for example, and will probably stretch out to about the orbit of Mars. So that means that our days are numbered. Those numbers are probably about 4.5 billion years old, years from now. So I wouldn't lose any sleep over it, but you get the idea. So when a star is formed, probably the most important number for any star is its mass, because that determines so much other information. It's going to determine how bright it can be. It's going to determine how hot it can be. It's going to determine its internal structure, which is what I have written up here on the board. It's going to determine its lifespan. Everything is related to mass. Its amount of gravity, how it dies is all related to its mass. And at the moment of birth, it will no longer pick up any new fuel. It will not pick up any new hydrogen or helium, and it will no longer put on mass after its birth. And so from its birth on is a steady process of getting lighter. All right, so let's look at what happens. First of all, a star that is too small will not actually form. It's actually called a brown dwarf, and they are so small that they basically they don't have enough internal temperature for fusion to happen. And so as a result, they never become a star. They're a failed attempt to becoming a star. And some of them have temperatures that are like the temperature that you might expect boiling water to be at. If you've ever burned yourself on coffee that's too hot, that's probably hotter than some of these brown dwarfs, because they don't have enough mass to build up enough pressure. As we're going to talk about in another video when we talk about the birth of a star, they don't have enough mass to build up enough pressure for fusion to happen. That magic number, astrophysicists have done all the calculations, is about 0.08 solar masses. Our sun is 1 solar mass. We use that as the reference point for all these other stars. So if it's less than 0.08 solar masses, then it will never become a star. It just doesn't have enough mass to build up the internal temperature for fusion to happen. But let's say it does. Let's say we have enough hydrogen that everything we have between 0.08 and 0.4 solar masses. That's going to form what's called a red dwarf. And red dwarfs, about 10% of the stars in our galaxy are dwarfs. And they have an interesting internal structure. All right, they have a core. All the fusion that happens in a star is going to be happening in the core. If fusion ever stops in the core, the star dies, it collapses, it explodes in about a quarter of a second. That's how long it takes for a star to die. And so a quarter of a second. The thing is, these tiny stars, they have that core, and then immediately outside that core, they have a bunch of convection going on. And a convection current, you may have taken another science class like a geology class or an IPC class in high school, or a physics class in high school or something like this, and you talked about what convection was. Just in review, convection is the movement of thermal energy by literally moving the hot stuff. In this case, what happens is you've probably heard the heat rises. Fire, if you've ever seen a campfire, the heat's always going up. All right, well, that's because the material heats up that gas, and that gas is now less dense than the gas around it, so it floats up to the top. And so that's called a convection. Well, what happens then is that convection, as it gets further away from the heat, some of that heat is dissipated, and then its density goes back to what it was as the gas contracts. All right, so it expanded when it was heat, starts floating like a hot air balloon, gets up to the top, starts cooling, shrinks, and then it falls back down. And that's called a convection current. And the neat thing about these red dwarfs is that all of their star structure is convection currents. And so as a result of that, these stars are going to burn a very, very, very long time. In fact, some of the red dwarfs in our galaxy probably date back to the beginnings of our galaxy 10 billion years ago. And so, and then when they do finally die, spoilers, they don't explode. They don't go through a second life. They basically, all the hydrogen is used up. It becomes helium. They don't have enough mass to fuse helium. So they become a big ball of helium that eventually dissipates and, floats out into the universe. Not very dramatic, but very long-lived. These guys live for a long, long time. All right. Our star is a middleweight star. It's between about 0.4 solar masses and 4 solar masses here. And this is what a typical yellow star is. And these stars are very long-lived. Our star is going to live to be about 10 billion years old. It is about 5.5 billion years old right now. So, we got another 4.5 billion years before we have to worry about anything. Our star is structured in a little bit different. So we have the core. Again, that's where all the fusion's happening. That's where all the excitement is. And then immediately outside of that core, we have what they call a radiative zone. Now, radiative zone is the material there is incredibly dense. And so it takes millions of years for light to escape from the core and get to the top of the radiative zone. And what's happening is that light is like it goes and it hits, it's like this photon, which is a packet of light, goes, it hits an atom, and then it's absorbed and then immediately shot out, but it may be shot out in a different direction. And so as a result of that, it's sometimes called the random walk. Right? It takes a very long time for energy to get out of the radiative zone. But the radiative zone is all external pressure. That's what's holding our star up. And then on the outside of that radiative zone, we have a convection zone. Just like these red dwarfs over here are convection zones. And that is much faster. The energy that once it gets out of the radiative zone, only takes a few months to get out of the convection zone. It's kind of like, imagine you have this huge crowd and then someone says, hey, I've got this great idea. Why don't we all get in a straight line so that we can get to the edge of the star? And all these photons go, yeah, sure, sounds good. Yeah, let's do that. Anyway, and then after that is still pushing out. So what's going to happen to this is that we're going to have a couple things. Number one is that we are going to develop layers. We have the potential in these middle-sized stars to develop not just a core of fusion, but on the outside, a shell of fusion of a different material. And we're going to see that on some of our medium-sized stars. All right. But that medium-sized star mass also determines its temperature. And so while our medium-sized stars are hotter, that's why they appear yellow, because they're giving off a higher energy photon as a primary wave carrier. And these red dwarfs over here, these guys here, they're going to die differently than the red dwarfs. Now, our really large stars are about 4 solar masses to about 200 solar masses. And these guys, again, we have that core, and then we have, it's kind of the opposite of our yellow stars. Right? These are these bright, giant blue, think Vega, think Rigel, some of these really bright objects in the night sky. And what you have here is you have a core, and then you have a convection zone, and then you have a radiative zone around it. And so these are huge stars, and they are going to, over their lifetime, develop a lot of different layers where you have core fusion, and then you have multiple shells of fusion where you may have silicon that's fusing into iron. You may have carbon that is fusing into magnesium and sodium. You may have aluminum that is fusing into iron. So you have a lot of different things going on here. These are the guys that when they die very dramatically. All right. These guys do not go quietly into that good night. They are going to rage against the dying of the light, to quote the British poet. Anyway, so that's kind of the basic structure of a star. By the way, there are no stars larger than about 200 solar masses. See, the heavier a star is, the hotter a star is, and because that star is so much hotter, it burns through its fuel much faster. These red dwarfs, these small stars, part of the reason they live so long is because they are burning their fuel, but they're burning it in a much slower pace, than a medium-sized, and definitely much slower than a giant. These giant, massive sized stars, these supermassive stars, are, by comparison, really short-lived, maybe even just a few. In fact, there's an equation that is basically you can calculate the approximate age of a star by its mass. Well, super massive balls of gas that are over 200 solar masses burn through their fuel so fast that essentially they form, they fuse, they explode, and they rip themselves apart in a matter of a few minutes. This is probably the only time we're ever going to see something like this is during the Big Bang. Is in the early ages of the Big Bang, there were probably millions of these things, if not billions and billions of these things, that formed, immediately went through all of their fuel, blew up, and seeded the universe with metals. And those then became kind of the great grandfathers of our current stars. All right, so I'm going to erase this and get this set up for a second here. So I've reset the board here because I wanted to talk about that internal power. I've alluded to it. I've talked about that internal power is going to be nuclear fusion, and all stars are going to start with the same type of nuclear fusion, and that's fusing hydrogen atoms. And so that hydrogen, of course, is going to be what they start with. That's going to be their starting fuel, and it is incredibly efficient. It is incredibly powerful, the amount of energy we're going to get from some of this hydrogen. All right, so in order for fusion to happen, the internal temperature of that star has got to be about 1,000,000 Kelvin. All right, that's a little under 1,000,000 degrees Celsius. And what happens is that protons have positive charges. And you may have heard in some of your other classes that opposites attract. And think about like taking a magnet. And if you take the north end of a magnet and the south end of a magnet, they want to stick together, don't they? Because they're opposite. They have opposite charges, opposite electromagnetic charges. But if I were to take that, take one of them, so now I'm taking the north end and the north end, and I try to push them together, there's some serious resistance there. Right? They don't want to touch each other, and when they do, as soon as I release one, it's gone. It's going to fly off because it doesn't want to stay there. So in order for fusion to happen, we have to have an extremely high temperature. All right, because at a really high temperature, what happens is, number one, is hydrogen, which is usually a proton with an electron zipping around it here, right? At a very high temperature, that electron is spun out and it's what we call ionized. And so now you have this bare naked proton, but it still has this very strong positive charge. And so it doesn't want to come together with the other proton, right? But again, if you can get that temperature high enough, they can slam into each other. And when they slam into each other, if they make physical contact, there is another force called the strong nuclear force that will hold them together. Okay, so with that in mind, this is called the proton chain or hydrogen fusion. Remember that a hydrogen nucleus is generally one proton. So what happens is we have this ionized proton. Over here, it's minding its own business. It's 1,000,000 degrees, so it's moving really fast through the core, and it runs into another ionized, very hot, 100 million Kelvin temperature proton. And they run into each other, they slam into each other, and they slam so hard that they stick. And one of those protons becomes a neutron. Remember that a neutron has no electrical charge, but they are important for holding the nucleus of an atom together. So what happens is when that happens, this gives off a high energy neutrino particle. A neutrino is just a high energy carrier particle for different things. And it gives off a negative electron. Now that negative electron, by the way, there's a lot of what we call beta positive radiation in a star. That's partly why stars twinkle, is now that beta positive. And so there's a bunch of positively charged electrons in the core. Those two are going to hit each other and they're going to give off some gamma radiation. That gamma radiation goes to help keep the core of the star hot. All right. So now, whereas we did have a lone naked proton, now we have a naked, what we call a deuterium. It's still hydrogen. It's an isotope of hydrogen, But this deuterium has one proton with a positive charge and one neutron with no charge. All right, so what's going to happen is it's still incredibly hot. There's still a huge number of protons floating around. And one of those protons, bam, slams into that deuterium, and it's going to form this little thing right here. This is a helium-3 atom. So now we've gone from hydrogen to now we're helium. And that helium, that's going to knock off another gamma radiation, and that gamma particle is still going to go, or that gamma photon is going to go towards keeping the core of the sun hot. All right? Some of those photons, by the way, do escape. Our sun does emit gamma radiation. It's just that gamma radiation is deflected by our atmosphere. I think I mentioned how in another lecture during class that certain substances are opaque to certain wavelengths of light, and gamma radiation in our atmosphere is opaque to it. So instead of passing through our atmosphere, it bounces off the surface, kind of like X-rays and a few other things. So now we have this, we call this this helium-3. All right. If you ask somebody, by the way, why we should go to the moon, sometimes they'll say, we think there might be helium-3 on the moon. And so I don't know about that, but that's what they're looking for. So that helium-3 is going to run into another helium-3, bam, super hot, and it's going to form a more traditional helium particle. And this helium particle, helium atom, sometimes called an alpha particle, is 2 protons, 2 neutrons. The extra 2 protons, they get bounced off, and they are now part of this cycle. They may get recycled up and become one of these 3 over here, and the process is going to go on and on and on. All right, where does the energy come from in all this? Well, the energy comes from something called mass loss. Albert Einstein, boom, Albert Einstein, probably most famous equation was E equals mc squared. Energy is equal to mass times the speed of light squared. In this case, the mass is the mass lost. So during this equation, and if you want to see the math on it, I'll show it to you in class, right? But during this equation, the helium that is formed right here is about 0.7% lighter than if it had had 4 hydrogens. So in other words, that energy had to go, that mass had to go somewhere. In this case, it was converted into pure energy. And it is a lot of energy. If we take 1 kilogram of hydrogen and convert it into helium, it will have a mass loss of about 4 grams. But that 4 grams multiplied by the speed of light squared, 3.0 times 10 to the 8th squared, gives us a number of 6.3 times 10 to the 14th, or if you like writing zeros, 630 trillion joules of energy. Now, we don't use a lot of joules in the United States. We use calories, but I went ahead and converted this over. That's about 20,000 metric tons of coal from 7-gram mass loss. So that 1 kilogram of hydrogen has as much energy as 20,000 metric tons. A metric ton is 1,000 kilograms. So that's a lot of energy. If you think this sounds really impressive, consider this. Our sun actually converts 600 billion kilograms of hydrogen into helium every second. So take 600 billion, multiply it by this number, and that tells you how much energy our sun is producing in a single second. It is a phenomenally, mind-bogglingly high amount of energy. And that energy, while it is true, that energy is spread out over all the surface of the sun, and the sun is a sphere, so that's a lot of surface there. All right, and only a tiny portion of it reaches the Earth. That's still enough to run the all the energy needs of the Earth. Like once, like if we could capture what actually hits the Earth, we could run 10 of our Earths on the amount of energy that we would have. We could meet 100% of our energy needs 10 times over if it really was just as simple as capturing that sunlight. Of course, it's not. You have distribution and construction and some things like this, but it's a huge amount of energy. So that is the source of that gas pressure. Mass is the source of the gravity pulling down on that star, but this is the source of that gas pressure. Now, this is what's going to start. This is for a red star, red dwarf. This is the only fusion they'll ever know. For ours, they're going to move on to another one that we'll talk on a different day called the triple alpha series. And this one and other stars, higher, more massive stars can get even hotter in their core, and so they can fuse even heavier metals. But this is by far the most efficient, and this is where it starts. And once this starts, a star is actually a star. Until this happens, a star is not a star. It is a protostar. It's a ball of gas. It may even be glowing because it's so hot, but it is not a star. A star is going to be a ball of gas held together by its gravity. And you have this energy from internal sources providing that gas pressure. That all that together is what gives the ball of gas its ball shape. All right, so I think that that's probably a good start on what is a star. There's another video we're going to make here in a minute about where stars are, how their stars are born, and later videos will cover their life on what we call the main sequence, and then their midlife crisis, and even their death. But those are going to be separate videos. This is where it all starts, and I'll see you in another video.